Okay, we'll continue our study of game theory. And let's look at another well-known game called the Battle of the Sexes. In it, a husband and wife are planning to go to the ballet or boxing match, and they would rather be together than be apart. Now, we have the extensive form of the Battle of the Sexes, starting with the wife's node. And the wife has two strategies or two options. She can either go to the ballet or to the boxing match. And the husband, who does not know what the wife's moves are, can also go to the ballet and the boxing match, right? Either the ballet or the boxing match, depending on where the wife goes. Their payoffs would be as follows. So if they both end up at the ballet, the payoff to the wife would be 2, and the payoff to the husband would be 1. If the wife goes to the ballet and the husband goes to the boxing match, they are apart, so their payoffs are 0. Again, if the wife goes to the boxing match and the husband goes to the ballet, they are apart again. So once again, their payoffs are 0, 0. If they both end up at the boxing match, then the wife's payoff is 1 and the husband's payoff is 2. We can represent this information in static form in a payoff matrix. And after we have done so, we can search for Nash equilibria by underlining the best responses. So when the wife goes to the ballet, the husband should also go to the ballet, and we underline his payoff of 1. When the wife goes to the boxing match, the husband should also go to the boxing match, and we underline his payoff of 2. Now, when the husband goes to the ballet, the wife should also go to the ballet, and we underline her payoff of 2. And when the husband goes to the boxing match, the wife should also go to the boxing match, and we underline her payoff of 1. So when we underline best responses, we find that there are actually 2 Nash equilibria. So this is an example of a game with more than 1 Nash equilibria, and there are no dominant strategies. It is possible for games to have multiple Nash equilibria. Now the question is, which strategy would be chosen? It is actually hard to say because the outcomes are quite symmetric. So the precise strategy, ballet, or boxing, it is difficult to say right now which of the 2 strategies would be chosen. Now let's look at another game called rock, paper, scissors. And in this game, scissors is greater than paper. Scissors cuts paper. Paper is greater than rock because paper can cover rock. And rock is greater than scissors because rock can smash scissors. And we can put all of the information into a payoff matrix again. So you have 2 players, P1 and P2, 3 strategies or 3 options, rock, paper, and scissors. And we can try to find Nash equilibria by underlining best responses. And when we attempt to do so, we note that we fail to underline both entries in any cell. So remember, whenever you're able to underline both of the entries in a single cell, that would represent a Nash equilibrium. In this particular case, we fail to do so. So this means that for this game, there are no Nash equilibrium strategies. It is entirely possible for a game not to have Nash equilibrium strategies. I would encourage you to try and find Nash equilibrium strategies in this game by underlining best responses. And when you attempt to do so, you will find that you fail to find any Nash equilibrium strategies. Okay, so moving on. This is another game and the payoff matrix, which is given below. So again, we have two players, and each player has three actions available to them. Player one has U, C, and D. Could be up, center, and down. We don't know. P2 has L, M, and right. It could be left, middle, and right. Again, we don't know. And the payoffs are given. And we can once again search for a Nash equilibria by, excuse me, by underlining best responses. And when we do so, we find that the strategy UL with payoff of 3-0 is a Nash equilibrium. And once again, I would encourage you to draw the payoff matrix and try to find the Nash equilibria by underlining best responses. And when you do so, you will find that the strategy UL with payoff 3-0 is a Nash equilibrium. There is also another way of finding Nash equilibria. So we are familiar with the underlining best responses way. There's another way. Now consider, so let's stick to the payoff matrix we have just seen and consider P1 first. Notice that for P1, the payoffs of D strictly dominate the payoffs of C. So 2 is greater than 1, 4 is greater than 3, and -1 is greater than -2. So P1 will never play C because it is strictly dominated by D. So we can get rid of C altogether for player 1 or P1. And when we do that, when we get rid of C, we end up with the following payoff matrix to the right here. And here we have omitted C altogether. Now, in this reduced matrix for P2, the payoffs of R strictly dominate the payoffs of M. So -4 is greater than -5, and 8 is greater than 1. And also the payoffs of L strictly dominate the payoffs of M as well, since 0 is greater than -5 and 4 is greater than 1. So P2 will never play M because it is dominated strictly by both L and R, and we can get rid of M for P2 altogether. When we do so, we get the following reduced matrix again. And again, notice that for P1, the payoffs of U strictly dominate the payoffs of D because 3 is greater than 2 and 0 is greater than -1. So we can get rid of D for P1, which ends up as this payoff matrix. And for P2, the payoff of L is greater than the payoff of R, which is, so because 0 is greater than -4. So we can eliminate R for player 2. And we end up with strategy set UL with payoffs of 3-0, which is just the Nash equilibria we figured out by underlining best responses earlier. So the process we have gone through is called iterated elimination of dominated strategies. And it is sometimes useful in finding Nash equilibria, especially if the payoff matrix is large. So if you have a large payoff matrix, if you can eliminate some rows or columns, the matrix becomes more manageable. And for the example that we just did, this payoff matrix, start with P2. We started with P1. You start the iterated elimination of dominated strategies. You start that process with P2, and you will end up with the exact same result. So I'll stop recording here.